Statistics is split in two parts. These are descriptive statistics and inferential statistics. We will have short explanations on both. Let's start with descriptive statistics. Descriptive statistics is a way to summarize data. Let's say we have several variables. So we want to have a single value that describes these variables and allows us to analyze these. It is indeed a useful tool because let's say we have 1000 examples, then we cannot observe the data directly. Examining a single value at a time will be very tedious task and impossible if we have data in millions. Hence, it is good to have one value or very few values that describe our data well. This measure is called statistic. The most famous statistic is the simple mean, also known as average. The mean, denoted by x bar, is equal to the sum of the values divided by the number of values. In machine learning perspective, a value represented by a feature can also be considered a candidate for statistic. The average is the measure of the center of the data. It allows us to see where the center of our data is. But a problem with mean is that it's affected by the outlier values. Let's say we have a feature whose value remains the same, that is equal to 1 for 99 examples. For one particular example, its value is 1000. Since all the values except one of this feature is equal to 1, it makes sense that the center is represented as the value 1. But if we take the average, the center will mathematically be equal to 10.99 due to one example, which is 1000. Hence, we say that the average is affected by the outliers. And this is primarily the reason why mean is not a preferred statistic to be reported for many tasks. What is preferred is another statistic, which is median. The median is basically the middle value. If we have a bunch of data or examples and we order the values and pick the middle one, this middle value will be the median. In case of even number of values, where there will be two middle values, the mean of these values become our median. We can think of median as 50% of the data is below the median and 50% of the data is above the median. So if we consider the case of 100 samples in our dataset with 99 ones and one example of 1000, which we talked about in the case of mean, the median will be 1 because in that example, 50% of the data is less than or equal to 1 and 50% of the data is more than or equal to 1. In contrast to mean, the median value did not get affected by the outlier value, which was 1000. This is the reason why organizations generally prefer to report the median of wages or salaries to have an idea of a typical salary inside the organization. Another value that is really useful is standard deviation. In case where the mean has to be reported, it should generally be followed by reporting the value of standard deviation as well. The reason to do so is because standard deviation is a measure of variation. It represents an average distance from the mean. We can see the formula of standard deviation, which is the square root of the sum of the distance from the mean that is put to square and divided by n minus 1. Standard deviation is useful because it allows us to have a complementary view on average, because the average gives us the idea of the center, but it doesn't give us the information on how widespread is the value of the variable or the feature. Standard deviation allows us to know if the feature is very compact, that is, all the values lie around the center, or vice versa, indicating if the values of this feature vary a lot. The last but not the least, correlation coefficient, also known as Pearson's correlation coefficient, when applied to two variables, help us in measuring the linear relation of the two. A variable related to another variable can be either positively related or negatively related. Positively correlated means that on average, if we take a high value of one of the features, the other one will be related to it and will have a high value too. Negatively correlated means that if you take a high value of one feature, on average, the other one will have a small value. It's usually in summarizing the relation between two variables. The value of correlation coefficient ranges from -1 to 1, 1 in case of positive correlations and -1 for negative correlations. And 0 indicates that there is no linear relation between the two features. To summarize, descriptive statistics are really useful if we have one or several features and we want to summarize them in a single value. Now let's try to understand a thing or two about inferential statistics. In contrast to descriptive statistics, where we have to have the availability of all the variables to come to a decision, in inferential statistics, that's not the case. The idea is to infer something by observing a sample of values, and not the entire population. Let's try to understand with the help of an example. Let's say we want to know how tall are the people in a specific country. Naturally, it is not feasible to measure every individual's value. Every individual's height. And to report the appropriate statistic, what we want to do is to measure the height of a certain percentage of people, let's say 10% of diverse population, one from every age group and ethnicity, to have a good enough idea of how tall people are in that country. The goal here is to infer or deduce on the whole population by observing a few. We will not go in detail, but the YouTube links in the slide are highly recommended to have a good understanding of the statistics widely used. Let's try to have a preliminary idea though. Simpson's paradox is an introductory way to show that if we use statistics and we are not careful enough on how our data is collected and how our data interact with other variables that we fail to observe, we can reach a false conclusion. It's important to keep in mind while analyzing data. Hypothesis testing is maybe the most fundamental inferential statistic. It's also called statistical test. It is useful to conclude whether a hypothesis can be rejected or not. Let's say we have a hypothesis that the height of all the people of a certain age group in a country is close to a certain number, and we want to test it, meaning that if we can reject this hypothesis or not. Another very important statistic is A/B test. To understand A/B test, let's take an example of machine learning. Let's say we have an old machine learning model that is deployed in production, and it helps in certain tasks, but lacks the performance. Let's say after months of hard work, we trained a brand new model that performs a lot better on our data. Although it's something to be happy about, but in reality, we just made sure that the model performs good on the old data that we have with us. We cannot be sure that if the data set that we have really represents what users will be input in the system. As we discussed before, the users can input lower quality personal images that we do not have access to. On these scenarios, A/B test can be useful tool because it allows us to have our new model tested for its performance in comparison to the old model side by side, but in a real environment. The idea is that we deploy both models and then users are split randomly to interact with these models. Their conclusions are used and performance is compared. Using the matrix that we are interested in, the user input is the key here. Another example is a recommendation system. YouTube also employs this system. So whenever we visit YouTube, we can see that YouTube recommends videos. We can see that, the click rate, meaning how many views the video has. So recommendation systems can also be compared using click rate, meaning in how many instances the user clicked on the video suggested by the model A versus the video suggested by the model B. Possibly, next, we can use hypothesis testing to test if both click rates are equal or if one is infinitely higher than the other, etc. It is useful to have a comparison based on the real data gathered from interaction with real users. It allows us to make decisions and back them up with statistics based on real user data.